Welcome to the EPG Padashala, the lecture series in computer science for the postgraduate program, and we are talking about the subject compiler design, and we are on module 34 where we will talk about code optimization. So, in the previous module we have looked at the position of the code optimizer, and this module the objective would be to discuss the optimization techniques in detail. So, the learning objectives of this module are to understand the function preserving transformation as a means of code optimization, to understand the need and ways of performing loop optimization. So, these are the primary objectives of this module, where we will be looking at dead code copy propagation, constant folding and loop optimization. So, the previous module we looked at the example quicksort function, and then we looked at breaking this quicksort function into 3 address code followed by converting it into basic blocks. So, the same example is carried out here, and this will be discussed in detail with respect to the optimization that is possible for possible at every basic block. So, this is the quicksorts module where it is an iterative situation. So, quicksort here, and so I will basically be calling here if n is less than or equal to m return, meaning that if you have only some component to sort, you will try to sort, else you will initialize. So, our first aim is to do the pivot situation here. The pivot is chosen as the first element, and we will be comparing that with every element in the array and rearrange. So, the while here is trying to basically keep on looping. This is a recursive call here actually, and these two do while is trying to rearrange such that rearrange till we are going to get a element which is greater than the pivot or less than the pivot. So, this is the position of swap. So, till that we have basically got here, and this is the quicksort recursive call. Now, coming on to the while loop is according to this break, where you have to have at least when the 2 pointers cross over, that is when you have done rearranging. So, that is what is the point of break over here, and there you will reassign and continue as a recursive call of quicksort with one half and the other half here. Okay. Now, this is being converted to 3 address code like this. We have already discussed enough about this 3 address code representation and how to convert this 3 address code, and we have also formed basic blocks from the 3 address code, where we have chosen the leader and the target of a conditional jump. So, as you could see, lines 1, 2, 3, 4 will form one basic block, lines 5, 6, 7, 8 will form another basic block, lines 9, 10, 11, 12 will form another basic block, 13 will be one block, 14 to 22 is another block, 23 to 30 is going to be another basic block. So, I have basically done these 2 basic blocks. Now, this 2 calls here are the 2 calls to quicksort, recursive calls to quicksort, where we will not discuss that in the recursive algorithm. So, our aim is to just look at this control flow for discussion on the optimization technique. So, this is what we have basically here. Now, for convenience, I have split the basic blocks B5 and B6 expanded versions are here. So, this is where we are going to start on optimization. Now, what we call as local optimization is the optimization that is possible within a particular block is called as local optimization, whereas optimization done across basic blocks is called as global optimization. So, we will first do local optimization wherever possible, and then we will try to optimize on we will perform basically global optimization. Now, the reason behind choosing these blocks B5 and B6 are B5 and B6 has got so many statements, and they are actually much I mean that requires optimization for sure. Okay. So, the other blocks, if you could remember, if you could see, they do not have much statements available. So, therefore, it is a better play. It is better to start from blocks B5 and B6 as an optimization metric. So, function preserving transformation is what one area of code optimization. So, as we already know that there are 3 optimizations which is definitely going to be required. One is transformation, second one is data flow analysis, third one is control flow analysis. So, we will start with the transformation where we call this as function preserving transformation. So, the typical transformations are common sub-expression elimination, copy propagation, dead code elimination and constant folding. We will see one by one in the context of the basic blocks B5 and B6 to start with. The first one is common sub-expression elimination. So, an expression E is called common if E was already computed and the values of the variables in E have not changed since the previous computation. So, I compute the value of an expression in a particular statement and till the same expressions available in the next statement, the values of the variables have not changed. If that is my situation, then I can basically eliminate recomputing of the same expression. So, this is called as common sub-expression elimination. As the name itself says, the expression is going to be common, okay, and we are going to get rid of computing this expression at multiple positions, rather reuse the same expression computed at multiple points of your situation. So, identifying E is easier with the DAG as a basic block where multiple tags can be associated. So, in one of the modules we have already discussed about construction of the DAG. So, similar to how the DAG is constructed, this identification of common sub-expression becomes easier. We will see again this in this module on how to locate it. So, let us see this. So, here T6 is equal to 4 into I, x is equal to A of T6, T7 is equal to 4 into I. Now, T6 and T7 are two expressions. The value of I has not changed between this point and this point. Therefore, we can eliminate that computation and wherever we are using T6 in place of that, wherever you are using T7 in place of that, T6 can basically be used. So, 4 into I is one common sub-expression available in this particular block. Similarly, 4 into j. So, between this computation and this computation of 4 into j, the value of j has not changed. So, therefore, I can reuse the computed value of 4 into j at this particular position as well as at this particular position. So, therefore, in the first scenario 4 into I can reuse the name T6 in place of T7 and for this one I can reuse T8 in place of T10. Okay, that is what we have done here. We have got rid of this T7 computation as well as this T10 computation and wherever was T10 that has been replaced now with T8. Now, this is with respect to basic block B5. Similarly, for basic block 6, I have computed 4 into I here and 4 into I here and 4 into j here. So, I can basically reuse this computation and then call it as 4 into I and 4 into n here. Okay. So, wherever we have used T11 that can be a T12 that can be replaced with T11 and wherever we have used T15 that can be replaced with T13. So, this is one more situation. So, 4 into n is going to be reused. Okay, global common sub-expression. Now, we have done local common sub-expression for blocks B5 and B6. Global common sub-expression is across basic blocks if an expression is going to be common and between these two basic blocks, if the values of the variables have not changed, then their expression could be reused. I need not recompute the expressions. So, on this basis, 4 into I is computed in block B2 and 4 into j is computed in block B3 and has not changed till B5 or B6. Similarly, 4 into n which was computed in block B1 has not changed till block B6. That is, the value of n has not changed, the value of I has not changed, the value of j has not changed once I am out of block B3. Okay, once I am out of block B3, the values of I, j or n has not changed. So, therefore, their values could basically be reused. So, this across basic block can basically happen. So, in addition to that, we have done a computation of A of T2 in block B2 and A of T4 in block B3. Their computation has also not been changed because T2 is simply computation of 4 into I and T4 is simply computation of 4 into j. So, therefore, it has not been changed. So, therefore, what happens here is this 4 into I has now been replaced with T2. So, therefore, T6 becomes redundant. So, wherever we have to use T6, I can use T2. So, that is what I have done here, A of T2. Similarly, wherever 4 into j has been used, that 4 into j is replaced with T3. So, but A of 4 into j is T4. So, I have got here A of T4. So, T9 is equal to A of T4 and A of T6 is equal to T9. So, A of T2 is nothing but, T6 can be replaced by T2 and so is the case with T8 where I can replace T8 with T4 to compute, to assign the value x to it. So, now this is what has been done because between blocks B2 and B3 the values of I and j hasn't changed after I am exiting out of B3. Similarly, once I enter B5, I am not changing the value of I or j. So, therefore, this 4 into I could be optimized across basic blocks where I can use the first computation of 4 into I computed itself as it is. So, that becomes A of T2 and A of T4 here respectively. Thus eliminating two more statements of the blocks B5 in the control flow graph. Now, one more optimization is A of T2 hasn't changed. A of T2 has been assigned to T3. So is the case with A of T4 which is assigned to T5. So T9 is equal to T5. So that is what we have done here. A of T4 is T5, but A of T2 is equal to T5, okay, and then A of T4 is equal to X. Now I have done something here. A of T2 hasn't changed. A of T4 will be changed only at this particular point. Now in place of T9, okay, in place of T9 I am also using T5. So we can come back to this optimization later, but as of now A of T2 is nothing but T3 and A of T4 is nothing but T5. That hasn't changed. So therefore that has been available as it is. Similarly for block B6, 4 into I is available from block B2 which is nothing but we said it is nothing but a T3. So I can say here x is equal to A which is equal to T2. So I can call this as x is equal to A of T2 and 4 into n is computed in block B1 which is nothing but T1. Therefore T14 is equal to A of T1 and so is the case with A of T2 is equal to T14 and A of T1 is equal to x. So A of T2 because T11 is anyway 4 into I, so that is replaced with T2, so I have done that optimization here. Similarly, A of T2 is already known to be T3, that is what we have used here, and T14 is equal to A of T1, so that is as it is. I am not there is no shorthand notation for A of T1 which was done in block B1, and A of T2 is equal to T14, that is the same thing, and A of T1 is equal to x, that is also the same thing. Now, assignments of the form, the next optimization is copy propagation. Assignments of the form f colon equal to g is a copy statement, okay, where elimination of common sub-expression leads to creation of copy. In the sense that when we got rid of the statement here, x is equal to T3, okay, and I have here A of T4 is equal, A of T1 is equal to x. X is equal to T3 and I have A of T1 is equal to x. Now, this is a copy. So, where I have replaced, I am now creating a copy statement. So, therefore, when you eliminate common sub-expression, that would result in what is called as creation of a copy statement. So, what is the elimination or optimization technique here? Assignment of the form f colon equal to g can be transformed as use g for f. Okay, that is wherever f was used, you can use g itself and get rid of this statement also completely. So, what happens here is I have to ensure that between this and this statement and the usage of f, the values of f and g should not basically change. If that is changing, I cannot use it, but I should basically ensure that the value of f basically hasn't changed. So, after ensuring that, I can use g in place of f itself. So, copy is introduced here. For example, I have a is equal to d plus e and b is equal to d plus e here, and I am computing c is equal to also d plus e here. How will this get changed is t, use a temporary variable t and convert this to a equal to t. So is the case with here, t is equal to d plus e and b is equal to t, because I know that this path or this path hasn't changed d or e, therefore I can reuse the same value t. Now this basically becomes c is equal to t. Now what is redundant? I have used a equal to t and b equal to t here. So therefore c equal to t will be a, C equal to t is a copy propagation statement. So when you eliminate common sub-expression, that will create a copy. So A equal to T is one copy, B equal to T is another copy, C is equal to T is also another copy, where instead of A, B or C I could use T itself. Okay. So that is the understanding here. Now let us take this example where we are on block B5. So this was your statement, x is equal to T3, T9 is equal to T5, A of T2 is equal to T5 and A of T4 is equal to x. So what happened actually is x is equal to T3, okay. So and T9 is equal to T5, okay. Now what happens is A of T2 is equal to T5. This is your statement. Now this T9 is equal to T5 becomes redundant because I am not using T9 at all. Therefore it has been taken off. Now this code is called as dead code. Okay, we will see that optimization in the next thing. Because of common sub-expression elimination, where you are getting rid of some variables, some statements becomes dead. They have to be also eliminated. So here A of T2 is equal to T5 is available. Now between this point and between this point, the value of x hasn't changed. So therefore in place of x, use T3 itself. So A of T4 is equal to x now becomes A of T4 is equal to T3 and A of T2 is equal to T5, that remains as it is. T9 is equal to T5 has been eliminated because that code is going to be called as a dead code. Similarly, I have here x is equal to T3, T14 is equal to A of T1 and A of T2 is equal to T14 and A of T4 is equal to x. So here what happens, T14 is equal to A of T1, okay. I am going to use T3 in place of x and A of T2 is equal to T14, okay, and A of T4 is equal to 3, okay. That is going to be the next statement. Now I am not reusing T14 here because it is anyway a temporary variable, so I am not reusing here, whereas here I am assigning it to a variable and then getting the value, therefore I have basically used that. Okay, a variable is supposed to live at a point where its value can be used subsequently, else it is assumed to be dead. Okay, if I am going to use a value of a variable at a later point, I will call the variable as a living variable, else I will call that as a dead variable. Now here x is equal to T3, this is dead because x is not going to be used and replaced, and hence it is replaced by T3, okay. So therefore we will say that x is not redefined, x is not going to be created, etc. Therefore we will say x is equal to x is not going to be used, therefore we will call this statement as a dead statement. Next one is called as constant folding. So common sub-expression elimination results in copies getting created. When you try to get rid of a copy, you will end up with some redundant statements, therefore it is going to be, it has to be eliminated. The fourth one is called as constant folding, where it is done deducing during compile time that a value is a constant and you can use the constant instead of the variable itself, that is called as constant folding. So when you already know the value of a variable A, okay, as a constant value only, wherever A is going to be used, I can replace that A with the constant itself for creating my code, or if I do not know that, I can basically use the optimization technique to replace the variable with its constant value. So here this would also lead to dead code. In that case what happens, we will result in again creating a dead code because I no longer require the variable and its assignment to a constant, okay. Therefore that is also going to be resulting in dead code. So this copy propagation elimination and constant folding elimination will result in dead code. Example is A is equal to 1 and C is equal to A plus B, for example say. Now wherever this value of A is used, I can use 1 in place of that. So A is equal to 1 and C is equal to 1 plus B. Now this is my statement, C is equal to 1 plus B. In that case A equal to 1 becomes a dead code because I am not using the value of A, rather I have already replaced A with 1. So therefore constant folding as well as copy propagation will lead to what is called as dead code, that is that statement has to be got rid of before and it need not generate any piece of code. So that is the conclusion here, where I say the statement A is equal to 1 becomes redundant and hence can be looked upon as a dead code, which needs to be eliminated for from generating code. Now, we can also use DAG for optimization, where the classic optimization possible with DAG is the common sub-expression elimination. Consider this following piece of instructions: A is equal to B plus C, B is A minus D, C is equal to B plus C, and D is equal to A minus D. Okay, to start with, I have B and C. I create two nodes B and C, and I create an interior node called as with the operator plus. I am labeling it as A. Then next computation is B is equal to A minus D. So, is there a node A already available? Yes. Is there a node D already available? No. Therefore, I will create it. And then interior node is a subtraction operator whose LHS and RHS will be the nodes A and D, and this is going to be called as B. Now, once I name this node as B, my previous B becomes B naught. Okay. Then next one is C is equal to B plus C. So, I have a new node called as B, I have a node called as C, and I have an interior operator which is plus, okay, and this new node is now going to be called as C, therefore, the previous node is assigned as C naught. Now, till this particular point there is no common sub-expression, though it looked as though these two are common sub-expressions. So, what we do here, because between these two statements, okay, the value of B has been altered, okay, that is very clear with respect to the DAG construction itself. Okay. The last statement is D is equal to A minus D. So, you normally have an RHS and an LHS. LHS is going to be computed as a value, RHS is referred to typically as a memory, as an address. So, I will compute A minus D as a value and put it into D, means I have to put it in the address of D. Okay. So, here A is available, D is available, interior node with a negative operator is also available. Now, this becomes D. After assigning this to D, I will rename this D, the old D to D naught. So, therefore, A minus D is a common sub-expression, hence it is evident from this particular interior node having multiple labels B, D. The next one is algebraic identities, which can be used to convert multiplication to addition, exponentiation to multiplication, etc. And you can also apply multiplicative identity and additive identity operations basically. So, x plus 0 is equal to 0 plus x is equal to x actually. We can look at x minus 0 is equal to x, so you need not even do this computation. X into 1 is the same as 1 into x, which is nothing but x itself. Again, this computation need not be done. X by 1 is also x, again that is not be done. X power 2 is x into x, okay. X into 2 is x plus x. So, that is also possible with respect to DAG, okay, where also you can use, we have already spoken about that in one module, where we said that you can also consider the associative laws or commutative laws to allocate registers for a particular node and then determine accordingly. That is also possible with respect to the DAG. Supposing there is already a left node, okay, and that left node is happen to be a right node of a particular arithmetic operation. If it is plus or multiplication, I can use the commutative law to compute that and then rearrange the left and right child of a particular interior node. That is also possible. Now, that is about transformation with respect to basic blocks. Now, loops basically forms the control flow, okay. In addition to that, the loop optimization talks about some optimization that is possible within the structure of a loop, okay. The running time of a program may be improved, the number of instructions in the inner loop is reduced. So, our ultimate aim is to reduce the number of instructions in the inner loop as much as possible. Inner loop is one which does not have any loop inside it, so that is the smallest possible loop. Outer loops could have more instructions and outer loops could contain multiple inner loops also. So, here there are three optimization possible with respect to loops. First one is code motion, the second one is strength reduction, third one is induction variable elimination. For example, look at this piece of code. While I less than or equal to limit minus 2, where limit is a variable, I is a variable, I have my body of the while loop here. If this has to be converted to a 3 address representation, how will this look like? I will compute L1 is equal to, because I have to do a begin label, T1 is equal to limit minus 2. If I is greater than T1, go to L2, and then I have the body of the while loop here, and then I have a go to L1 here, and I will have L2 here. Now, supposing say within the body of the while loop, the value of limit is not going to change, okay, the value of limit is not going to change, then this computation limit minus 2 has to happen as long as the while loop runs. Supposing this while loop runs for some n times, then limit minus 2 also has to be computed for n times, which is going to be a waste of computation. Therefore, this can be optimized. This is called as code motion. Check for movement of code within the body of the loop. If a particular variable's value is not going to change, and if that is computed as part of the expression, then you can eliminate that and put it ahead of it. So, how do we change this? So, for that we will compute t is equal to limit minus 2, because limit is not going to change anyway, okay, and then we will compute while I less than or equal to 2, and then I will have my body of the while loop. So, how does this translate to a 3 address code? Outside this I will have T1 is equal to limit minus 2, I will have this label here, I will then have the body of the while loop here, and then I have a go to L1 here, and L2 will be here. Now, this body alone gets executed for as long as this condition is satisfied, but limit minus 2 gets computed only once, okay. So, therefore, this is going to be the optimization that is possible, where if a particular expression is computed multiple times because it is part of a loop, then, and if the value is not going to change, move it outside the block, typically move it up front, move it to the previous block basically. So, the next one is called as strength reduction, where you can replace complex multiplication or division with respect to addition or subtraction. For example, here T4 is equal to 4 into j, and j gets reduced by 1, okay. Now, the value of j is going to be reduced, no doubt, but this is multiplication, okay. So, what I can do is I can convert this multiplication, I can do this outside, okay, and then what I can do is I can decrement j, and then I can simply say T4 is equal to T4 minus 4, because first time, for example, j is equal to 10, this 4 into j will be 40, next time j becomes 9, so 4 into 9 will be 36. So, the value of T4 gets reduced by 4, okay. So, I am incorporating that here, T4 is equal to T4 minus 4. Now, in the process what happens? J becomes a dead code, okay, here. So, I am just pointing out the parallel transformation which you already know. So, j is equal to j minus 1 here, which becomes a redundant code. So, therefore, T4 is equal to T4 minus 4. So, what have I done? Rather than multiplying it for some n times as long as this loop executes, we have moved this code ahead of this, therefore, it gets computed exactly once, whereas here it is replaced by n times of subtraction. This is called as strength reduction. Induction variables control the loop iteration, therefore, that should be taken care for doing that. The last one is induction variable elimination, where the loop indices can be typically I, j, etc., and they could be eliminated if the value of I and j is not going to be required later, okay. So, for example, here this I and j is going to be used here, but if you remember, the next block B4 will be like checking on I and j, okay. So, rather than that, what we can do is, in that case I and j becomes essential, okay. So, I have converted this block to something like this, where I have moved 4 into I to this block, 4 into j to this block, and this will simply add by 4, this will simply subtract by 4. So, I have basically reduced my basically done here strength reduction, where I have replaced multiplication with addition here and multiplication with subtraction here, okay. Now, the last point will be, this was a comparison between I and j, okay, where I have now got, we already know that if you look at this block, we already know that I is equal to I plus 1 and j is equal to j minus 1 becomes redundant here, becomes dead code rather here, because I am not using the value of I and j in this block at all. But the next block was comparing between I and j. So therefore, rather than comparing it with I and j, I can use T2 and T4 itself for comparison, because T2 and T4 indirectly reflects I and j, right. So T2 is equal to 4 into I, so for example, if I is 10, T2 will be 40. If j is 6, T4 will be 24. So I will be comparing 6 with 10 normally. If I get rid of I and j here, what will I be comparing? I will be comparing T2 and T4. Rather than comparing 6 and 10, I am comparing multiple of 6 and multiple of 10 by 4. Okay, again it is a common constant factor, therefore I can do that. Okay, so I will be comparing T2 and T4, and that is what is happening here. So this block had only 4 statements. Now it has got these 2 additional statements, which was moved from B2 and B3 here. So this had 4 statement. I got rid of one, which is the induction variable. Again I got rid of an induction variable here, because I am not going to be using I and j later. Therefore that was got rid of, and I have replaced here computation of T2 with T4, comparing T2 with T4 rather than comparing I and j. And these you can remember that it has basically around 8 to 10 statements. Now it has got only 3 statements in both the blocks. Okay, so that is the optimization which I have basically done. Now on to summarizing. This module we have talked about the basic function preserving transformation, like code common sub expression elimination, copy propagation, constant folding and dead code elimination. We have also seen some algebraic transformation and the DAG based representation of basic blocks for common sub expression elimination also. We have also done loop optimization, where we have looked upon induction variable elimination, strength reduction and code motion. Thank you.